container technical field committee at AWS. And so long story short, I actually spend a lot of time with EKS and Kubernetes and containers and ECS and all the things containers. And so like I kind of mentioned, Mars came to me and said, hey, Bryan, what do you think about doing just a presentation? And I was like, all righty, sign me up. So here we go. This is going to be probably about an hour long. I might actually go ahead and cut myself off at certain points and times because what I'm going to do is I'm really going to dive into this. I want to deep dive. I want you all to have a good time. So sit back, relax. But yeah, I'm going to try to talk a lot. I might be going through a lot of material, but it's just because I want you to really get that breadth and depth that I feel people really enjoy when they come to these types of community events. So just to kind of kick it off, if you've never heard of the container, don't worry. That's actually what I'm here to help for. But just so you all know, a container is a lightweight, standalone, executable package of software that includes all the dependencies inside of it. So that could be your code, that could be your runtime, that could be anything, right? And basically, if you didn't really know this, containers really changed the world. I mean, completely. It is taken by storm, and there's a lot of different versions of containers as well, right? And it's really had a long history from Chroot, jails, Solrs containers, LXC, and so on and so on. But I would say, basically this idea that I can actually literally kind of put a box around my application and able to basically deploy it anywhere is really, really powerful. And Docker really helped with this because if you did not know this, when you've used Docker, it's basically combining 6 or 7 different types of Linux processes in one. And so Docker is really known for the developer experience, and that's why they became so popular in this type of ecosystem. But there's container, there's Rocket, there's Podman, there's all sorts of different types of ones. But what's really important about this kind of conversation is what does containers really provide? And I promise we're going to get super deep into Kubernetes in a second, don't you worry. But basically, if you've ever dealt with containers before, you have definitely seen this slide. And it's because you have to kind of understand what the difference is between VMs versus containers. On the left-hand side, the thing about VMs is that you still have your server, right? You'll have a host operating system that might be Linux, that might be something like Windows, but then you're going to have to use something like a hypervisor that would actually let you deploy your VMs on your computer, right, or your server, whatever have you. The problem is that there's a lot of overhead. You have your guest operating system, and you have to run that operating system, and you also have to patch that operating system. And if you've ever looked at the slide and wondered what it meant by the bins and libs that I have right here and I'm kind of highlighting, that stands for binaries and libraries. And the thing is what you notice with the VM side is you actually have to make sure that your bins and libs, or your binaries and libraries are installed inside that VM. Compared to the right-hand side with containers, because of the way that they're made, you can actually share specific aspects of your binaries and libraries inside of your Docker images, or even during your runtime, depending on how you build this out. If you look at the right-hand side for the containers, you'll notice that the containers, all you need to do with containers is basically just have a server, a host operating system, some kind of content manager, which would be in this case Docker, and then there you go. You can actually let different types of applications utilize those binaries libraries together, right? So what you can do is kind of spawn these applications off of this. If you've never really seen or built or worked with Docker before, this is actually kind of how this ecosystem works. And this is literally what would be installed on multiple machines, even your local machine per se, right? At the left-hand side, you would have your client, your Docker client. That would be usually some type of CLI, right? Basically, you would have 3 major commands, but by the way, there's tons of commands. I'm just kind of talking out loud. But what you would be able to do is say Docker build, Docker pull, Docker run. What's really happening is your CLI or your client is actually hitting this Docker host, right? This might be on side of your computer. This might be outside of your computer, right? This might be on a server far, far away. But nevertheless, that client is literally just hitting that Docker daemon, And that Docker daemon is what is managing all this infrastructure for you. So for example, when I say Docker pull, it would be actually pulling from the Docker daemon through a registry, right? If I said Docker run, that would actually take an image, a Docker image that you might have written out by hand, and then actually turn it into a container, right? Image running by itself is a Docker file, and then containers running would be the actual running point of that. And then last but not least, all those images are actually stored into a registry. So that could be Docker Hub, that could be Elastic Container Registry, that can be any place, right? Self-hosted registry, and that's kind of how this kind of ecosystem works, if you've ever been curious. Now, I really want to kind of dive into the Kubernetes side. But I just wanted to kind of talk about overall what the container landscape looks like. And just kind of know, I really love our container services team, and I am actually not part of the actual service team in any way. I'm actually a solutions architect, so I spend a lot of time with, developers and operators and development teams, and then I deal with extremely large enterprises. But that doesn't matter, because the thing is we have an awesome, awesome group of people at AWS that continuously keeps building and pushing and working together, and it's a great type of ecosystem. Now, the thing is I'm just going to show these 3 basic slides, and then I'm just going to go into kind of the compounding components of Kubernetes. So I'll start with the top left, and then I'm just going to kind of work my way down. So if you've ever wondered how we at AWS look at our container landscape, it's kind of like this, right? Top left would be the Elastic Container Service. This is actually our managed service that we have at AWS. And it's fantastic. Basically, what you can do is actually spin and orchestrate containers, and you're only paying for the EC2 instances that you use underneath. What's really interesting too is we actually have something like capacity providers where you can actually have a mix of on-demand and spot instances, and the infrastructure layer will handle everything for you. What's also really awesome is that you would actually have Fargate Spot. So if you are having stateless containers, you can actually utilize Fargate Spot and Fargate as well, depending on how you have your application set up. If we go, and I'm just going to skip right over the EKS part, I think that's the big section. But if we went to this layer, on the middle layer, it's really important that I always kind of mention this, and I will be talking about EC2 and Fargate a little bit extra. But basically, what I'm saying is this is your infrastructure as a service, or possibly your infrastructure layer, or what you're actually spinning up via nodes. So when I say EC2, basically I'm saying that you can run your pods onto EC2 instances, or now you can actually deploy your pods onto Fargate. If you've never heard of Fargate, Fargate is our serverless compute engine, meaning that you don't have to deal with any servers underneath, right? You just have to deal with your pods or containers. It's a really great technology. I'll be talking about it a little bit more in depth in a second. Last but not least, we have our ECR, which is our Elastic Container Registry. This is kind of like where you can actually store your Docker images if you need to. It's highly scalable, and it's backed by S3, and it's being used all over by hundreds of thousands of customers. And also, by the way, now it does support Helm charts. So be aware that you can actually store your Helm charts into ECR as well, and there's free image scanning. A couple other things real quick. I just wanted to mention Cloud Map. If you've ever had problems, or you're wondering how you can really work with service discovery on AWS, this would be a really good way of utilizing this service. Basically, this is a 300,000-foot view of your endpoints, and you can actually constantly monitor these health of the resources, and it's really meant for just service discovery. So if you ever have problems with that, I definitely suggest to check this out. And then last but not least, before I kick it right into the high gear, I just want to mention App Mesh. This is actually AWS's versions of a service mesh. If you ever needed to try something that I highly recommend it. It's a managed service mesh. So the actual control plane would be in one of our regions, and then you would deploy your sidecars as on the sidecars. But yeah, we just actually started supporting circuit breaking, and there's going to be a lot of good things coming around reInvent as well. But it's great for tracing and so on. Okay, now Like I said, I always find it really important that we kind of talk about the underlying layer first before we dive into the Kubernetes ecosystem. And the reason why is because there's just so many different things that kind of come into play. And I want to give you the best practices while I'm kind of walking through this. Now, you're looking at the screen and you might be like, what is this guy showing me? Basically, just long story short, I am showing you how many different types of instances that we have and how many different types of variations that we have. Just know when you use our EC2 instances in our servers, and basically if you're kind of new to AWS, you may not know what I'm talking about, but this is our VMs, our EC2 instances, our nodes. But what I'm saying with this screen is that make sure that when you're using Kubernetes in general, that you are purposely right-sizing your instances. Make sure you're using the right ones, right? And if you ever need, faster processors or better instance storage or, accelerated computing, you can actually use these things. And remember that the networking goes up to 100 GB, right? Make sure that you're utilizing this, because the reason why is I work with customers and they just didn't realize that they made it wrong. They made it pick the wrong instance, right? And nevertheless, be sure to know that always you have the inference and EBS and so on and so on. When it comes to the CPU architecture, I think that's also really important. We support Intel, AMD, and then we last but not least support our new ARM chips with Graviton 2. I have a small comment. We all get it. These are our CPUs that we help support at AWS. I will say those ARM instances have been great. Basically, we came out with our own chip for a company that we acquired a while ago named Kernel Labs, and now we have ARM instances. And so basically, you can actually switch, say, for example, to a T2 medium to one of our ARM instances, and you can save about 20% of your money, and then also get about 40% increase. The only big thing that you would have to kind of change is possibly recompiling your packages with ARM instead of an x86. So I would definitely check this out. Honestly, this is a really quick way to save a buck or two. And yeah. So the one thing I wanted to mention while I'm kind of discussing EC2 is how we kind of have this built out on our layer inside of our regions. And by the way, our regions are highly scalable, infrastructure around the world. And inside of our regions, inside of these availability zones, we actually have what you see here, which is basically we have deconstructed our plane and made it where basically we can independently scale up and down some of these infrastructures. So for example, if you needed more storage or needed more compute, that's how you're able to independently scale these things up and down. Yeah. So when it comes to Fargate though, it's a little bit different story. The difference with Fargate is that before with EC2, you're still going to have to actually deal with servers, right? With Fargate, this is a completely different type of architecture. If you actually think back to what I was talking about when I said VMs versus EC2, this is kind of like a VM. In fact, this is a micro VM. And the thing about Fargate, again, is completely serverless. We handle the infrastructure for you in the back. So we can independently scale you up and scale you down depending on what you use and how you set that up. And you only pay for what you use. And I bring this up because the technology behind it is really fascinating. We're actually using something called Firecracker on our backend. And by the way, Firecracker is actually open source. You can go to GitHub right now and type in Firecracker, and you'll actually see us, pushing this out to the open source community. But basically, this is built on KVM. It's on the same hypervisor as EC2 Nitro. That's what I just showed a second ago. And yes, these micro VMs, it's hundreds and thousands of millions of these little micro VMs that can spin up in less than 4 milliseconds. And by the way, there's strict isolation between these VMs, and that's what makes them so nice and so secure. And last but not least, if you're kind of curious what this looks like from this kind of a more technical point of view, basically this is what's going on. you kind of are, we're actually using a CLI that actually will hit a RESTful endpoint and actually kind of scale these micro VMs up for us on our back end. Again, kind of independently scaling out what we need to. But nevertheless, we make sure that there is a jail barrier and it's configurable. So when you are picking out your Fargate task, if you've ever noticed how you can select a certain amount of CPU and memory, it's because this is how we're actually locking this down. You get what you choose, right? And it's great for multi-tenancy. So one last thing to kind of kick us off in this direction, I always think that's extremely important, is remember that when you are looking at containers at AWS, I always recommend to start from the very top. Decide if you want to go to ECS. And by the way, I want to be very open. You don't have to use ECS or EKS, right? This is your choice. You can do whatever you would like. But if you were looking at managed container services, I suggest determining if you want to go through ECS or EKS, right? And then from there, you need to decide how you want to deploy your launch type, right? Kind of to my previous slides when I said containers on AWS, this is where you would be like, okay, do I want to use Fargate or I do want to use EC2? And then you move from there. And last but not least, just to kind of kick this done, sometimes I'll have a little bit of this infographic where I kind of break down which parts are actually good. If you should use EC2 or if you should use AWS and what those trades off. Sometimes you like presentations, I know I do sometimes, but sometimes I just need a literal chart to be like, what is good and what is bad, or not even that, is what's the trade-offs, right? But yeah, this is kind of where I would come into play and say, if you want to run your own infrastructure by yourself, you should try EC2. If you want to not even manage servers, you should go and try out Fargate. Okay, Kubernetes. So we already kind of talked about how that Docker ecosystem kind of works. With Kubernetes, you don't have to worry about that Docker client anymore on the left-hand side. What you're actually using is something called kubelet, right? Kubelet is actually interacting with the Docker daemon. So basically, instead of you running your CLI commands by hand, not like you would, especially on the production system, but you would actually be using kubelet, and this agent would actually be, utilizing these services for you. And so what happens is instead of having multiple and hundreds of containers in different areas, Kubernetes is actually using these agents to actually manipulate these Docker hosts. And it all reports back to the main control plane, right? So the control plane is continuously talking to kubelet, kubelet is continuously talking to the control plane, and it is acting on the behalf of you, and your Kubernetes clusters is spinning all this infrastructure up for you. And so it kind of looks like this. And I might have an extra slide up here coming up soon, but this is actually the entire Kubernetes basically architecture that you actually see and deal with. I'm going to kind of start from the top and kind of break my way down. I might have an extra slide on here on accident with this, but I think it's a good time to kind of break down how Kubernetes works and what the infrastructure layers are kind of like. So I might have to walk a little bit with my mouse, but that's okay. So when you are dealing with Kubernetes, remember that these top components are actually installed into that control plane, right? If you think back, so you have etcd, you have manager, you have, and so etcd, by the way, is a data store. This is actually what keeps the state of your Kubernetes cluster. Controller manager, this is actually looking at the state of your cluster. And so basically, if you take it kind of like this is how I like to describe this. Kubernetes actually took a lot of lessons from robotics. And basically, think of a robot. You would say, Mr. Robot, go pick up a tennis ball. That last command that you just told that robot to go do, pick up the tennis ball, Johnny 3000, he's just going to continuously keep trying to grab that tennis ball, right? It's going to keep trying to make the state happen. The same thing occurs with Kubernetes. So if I say Kubernetes, I want you to spin up 5,000 nodes, it's going to literally keep trying to continuously spin up those nodes unless it breaks off or so on, or there might be failures or there might be pauses in the launch. But nevertheless, that's the power of Kubernetes, because once I tell it to turn into a specific state, it will continuously keep doing that. And then when anything gets out of that state, it will try to fix that state for you. That's why it's so powerful. On the left-hand side, on the cloud controller, this is actually what all the cloud providers are actually building into the master, or the control plane area. So basically, when you are saying, Kubernetes, I would like a load balancer, it would actually hit that cloud controller that you see here and actually say, okay, I would like to go set up a load balancer, so I'm going to go hit up AWS and spin up an ALB or an application load balancer or a elastic load balancer. And so that's how it's actually talking to the cloud. Now, on the left-hand side, though it's very simple, the scheduler is meant to schedule everything out. So when you say, I want to launch a container, in this use case, actually, you would say pod. It would actually go and find the instances and deploy those pods onto that infrastructure. And it also looks at this by labels, and that's really important. Last but not least, the kind of breakdown. So the top part would be the control plane. This bottom part would be the data plane. These would be each different types of nodes. In my use case, at least with AWS, that would be EC2 instances. But every EC2 instance would actually have the components that are installed here. So kubelet would be actually talking to the API server. Kubeproxy is actually in charge of proxying the network layer to all the nodes. So that's how it's able to talk to every single one of another. AWS node, that's actually the CNI plugin, which is the container network interface for AWS. So you can have some connectivity. Last but not least is going to be the kubedns, which helps the DNS resolution inside the clusters. And then last but not least is going to be a container runtime. And that container runtime would be Docker, right? So kubelet would be talking to Docker in this use case. But nevertheless, I kind of sped through that. But this is kind of how the Kubernetes clusters are always set up. Now, when it comes to AWS, we have about 51% of these Kubernetes workloads on our infrastructure, and our customers are really, really enjoying it. And by the way, I believe that survey's a tad old, but nevertheless, we see hundreds and hundreds and hundreds of thousands of customers helping and coming to deploy this out. So I know we went over the state a little bit, but for everyone that's on the call, just know that Kubernetes is an open source and governed orchestrated by the community, the CNCF, exactly why we're here. It is a fantastic community, by the way. It's pure upstream. It's a really good experience. Kubernetes is governed by the people, and it's such a fantastic system. Also, the orchestration system, if you want scale, here you go. Kubernetes is so powerful. You can literally say, spin up as much infrastructure as you want. And we're actually even seeing Kubernetes spin up AWS infrastructure or, other types of things, and letting the Kubernetes cluster handing out the infrastructure rather than saying Terraform or CloudFormation. But nevertheless, it is super powerful. And then that very last point, I've already kind of talked about it, is the Johnny 3000 story, but basically just remember, Kubernetes is always continuously watching the state of your cluster. So when you tell it to do something, it will do it automatically, and it'll keep trying to make sure it's at the state that you said it was, especially the declarative part. So we already broke this down one more time. This was the control plane and the data plane. The biggest thing I did not really highlight, though, was etcd. Etcd is extremely important in this scenario, and it's where you're keeping your state, right? So basically, all these commands that you're telling the Kubernetes cluster, it's all being stored in etcd. Etcd is actually a data store, meaning a quorum data store, meaning that it has to have 3 instances of etcd running at all times, and it will actually do a quorum to actually nominate whoever is the primary, and then actually send the information to the secondaries. If you lose your etcd cluster, it's a bad time. You lose your state, and it's hard to kind of deal with. We've already had this. Basically, I was going to go through the same infrastructure again. My apologies for this extra slide. And yeah, okay. So running Kubernetes on AWS. So I just want to fully say that, while I'm talking to you, I'm just trying to give you all the information that I kind of see, right? I'm very blessed, and I have some of the greatest customers I've ever worked with. In fact, some of them are like, hey, we're going to tell you how to run Kubernetes, Bryan. And I'm like, thank you, I needed that. But I just want to make a point that there are many tools to run on AWS. You can use Kops, you can use Ansible, you can use KubeAdmin. It kind of depends however you want to, right? Sometimes you don't need a managed service, but in this case, that's what I'm here to talk about. When it comes to local development, a couple things I see is Minikube. I get this question a lot, so I just kind of wanted to just kind of tell people what I see. I see Minikube a lot. Basically, this is just a way to have a little bit of a local environment. I personally use Kind in my environment. Basically, this is just Kubernetes in Docker. It's really awesome. I really enjoy Kind. It's really cool. I suggest checking it out if you've never used it before. And then last but not least, you can absolutely use the Docker desktop to actually spin up Kubernetes on your local environment. And then last but not least, before diving into, I believe the next one would be the EKS portion, is sometimes I get asked about tools for local dashboards. And so I just wanted to say, of course, you have a vanilla Kubernetes dashboard that you can spin up. I see a lot of people use that. I personally use Lens. If you've never used Lens before, it is really awesome. This is actually it. I actually was looking at a couple of clusters recently, but basically just kind of zoom in because I know we're all getting a little old. I hope I can zoom in. It's not working right now, of course. But basically, this is just a way to look at your Kubernetes dashboards, and you get a nice little view. And it's actually reading off of Grafana, right? So you can see my daemon sets, my states. You can see all my pods that are running. I'm actually running Argo CDs, stuff like that. Here's the AWS nodes that I was talking about. This is just a normal cluster that I have some demos running in. But yeah, I really recommend checking out this dashboard. It's really cool, especially for the fact that you can actually bring up your own terminal and actually connect to your pods, right? So if you really want, you can just actually see what's going on. So, yeah, and by the way, Octane's really good too. Just not, that's my personal favorite, but I've used Octane as well. Okay, so when it comes to EKS, we are seeing a lot. It is so much fun kind of seeing use cases and the ways that customers utilize EKS on AWS. If you're wondering why I'm randomly just showing you pictures of some clip art that I might have found randomly, it's because these are actual patterns that I see a lot. Right, absolutely. You see microservices. You know, containers are polyglot, meaning that you can have multiple languages talking to each other within your containers. Right, you can bring whatever you want. Platform as a service, that's actually my personal favorite right now. Basically, you have infrastructure teams building platforms and helping send infrastructure out to all their teams around their organizations. It's a really interesting problem, and that's actually one of my favorites to kind of track. Enterprise app migration, absolutely. And then last but not least, machine learning. That was actually probably our biggest shock when we first originally launched EKS. We just started noticing everyone was using training jobs on EKS when it first started. We're just like, wow, we just had no idea. And now you have awesome things like Kubeflow, and you have all the mass migrations from the open source community. It's really cool stuff. So when you are dealing with EKS, it's a little bit different. I mean, now when I say a little bit different, your control plane would actually be on our region, right? You wouldn't actually manage that control plane by yourself. And just know, by the way, this is completely upstream, completely certified, conformant version. We're not adding proprietary software into the ecosystem at all. We support 4 versions of Kubernetes at any time, right? So we are continuously updating and working with the Kubernetes ecosystem. And then also, last but not least, we do support the upgrades and worker nodes and the control plane. And nevertheless, we are certified Kubernetes, and we work closely, very closely with the Native Computing Foundation. And so, yeah, basically, you would actually see on your right-hand side, you would use kubectl or kubectl, depending on what religious war you're in. All jokes aside, there's many different ways to say it. I say kubectl because it makes me feel like I'm cool. But you would actually have an endpoint, and then your endpoint would actually talk to those different worker nodes. So it kind of look like this on the right-hand side. Now, if we work and we look into the control plane, right? Because I get a lot of questions like, okay, if the control plane is managed in the back, how does that kind of work? And this is actually how it works. This is what it looks like. If you actually kind of come back to this slide, this little endpoint that we were looking at, right, is actually an API NLB endpoint. And basically what it is that endpoint is actually funneling traffic, this load balancer is funneling this traffic to that managed control plane on the regions. And then from there, we're actually funneling the same traffic into an etcd cluster as well. And we actually manage all this infrastructure for you, and you can't even mess with it. And it's all AWS native services. So, you know, we're quote unquote eating our dog food, as they say. So basically, we're using our own infrastructure to spin up these things on our back end. And yeah, it's dedicated control planes for each person, or each account or launch. Now, there's a lot of text on this screen. I just want to say basically what this is and what this means is this is the current versions of supported Kubernetes that we currently support. So right now we support 1.18, 1.17, 1.16, which is a massive update, by the way. Hope you change your APIs a little bit. And then last but not least, we're currently supporting 1.15. Yeah, and yeah, there's major changes always coming. We definitely fast follow as much as we possibly can, but as we all know, the Kubernetes ecosystem is a little fast. Not gonna lie, it's awesome. So when you are working with the data plane, right, you have a choice of how you want to deploy your instances or your nodes. So I usually tell my customers you can kind of look at it 3 different ways. The first way would be bring your own EC2 nodes, right? What that means is you can actually use this Kubernetes cluster to spin up these EC2 instances, and you have full reign to configure them as much as you want. I see a lot of customers use this with Terraform because they want to be able to bring their own custom AMIs and utilize this and everything with their auto scaling groups. The problem is, though, is you still have to deal with the patching in the operating system. The next one, though, in the managed node groups, basically we actually manage the nodes for you. You would actually have to spin up those nodes and that infrastructure by yourself. With the managed node groups, we actually just handle it for you. And so you could not actually bring your own AMI. That has changed. You actually now can use custom launch templates and actually bring your AMI to the managed nodes, and then it will spin up the infrastructure for you underneath. And I've actually seen a lot of adoption to that, and I highly recommend my customers switch to managed node groups, just so you don't have to handle the updating, the rollout, and so on. And then on the right-hand side, obviously, we just kind of talked about Fargate a little bit. You can actually use EKS to spin up your Fargate containers or excuse me, your Fargate deployments, and actually just launch your pods onto them. Again, you don't handle any of your infrastructure underneath it. You're just literally just running these pods. And also now, just when you're working with the data plane, we have a lot of good and huge, rich ecosystem, just like Kubernetes does in general. But I always recommend to always grab an EKS AMI that's optimized. It's real quick, GitHub search, possibly taking that and making your own AMI, depending on how you set up your golden image. We also have deep learning containers, and we also run containers on Windows. And so I see sometimes heterogeneous clusters, meaning running Windows and Linux at the same time within their own clusters. It's awesome. It's really good stuff going on. When it comes to security, I just want to make a quick note that we actually have this new Amazon EKS CIS Benchmark. And basically, this is a benchmark that was made by Aqua that you can actually use to use the CIS benchmark against your EKS clusters. So I highly recommend to actually add this to your CI/CD pipelines in some way so that you can make sure that your clusters are secure, right? Because the last thing I ever want anybody to deal with is a bad day. This is actually another part that is something a little bit newer as well. This is actually what is called Bottle Rocket operating system. If you've never heard about this, if you don't care, that's cool too. But Bottle Rocket is an actual open source Linux-based operating system specifically meant for containers. And what you can do with this is actually update your containers in a nice, secure way, basically through APIs. And it was actually written in Rust using the update framework that was actually graduated in CNCF. But nevertheless, I highly recommend if you're just trying to find how do you basically pick an image or an AMI for your cluster, I recommend kind of looking at that. EC2 support, we've already talked about this a lot, but basically you can use any kind of type of EC2 you want to. It's up to you, right? I highly recommend you use spot instances. I really recommend, saving money where you can, and especially for your stateless applications. If you are a customer and you're using a lot of compute, I suggest to also do a compute savings plan. Basically, this is a way to commit to a specific amount of compute, and then we'll give you a certain type of discount. And then last but not least, know that you can run on Outpost, Wavelength, and a bunch of other different services. When it deals with managed EKS node groups, this is kind of how this works out, but just remember when you're dealing with EKS managed node groups, know that it actually associates an auto-scaling group with the cluster. You can actually use an EKS optimized AMI, you can use Ubuntu if you would like, but to my earlier point, you can now actually use custom launch templates and actually bring your own AMI, right? So again, I really suggest my customers to actually switch this because it's just another way of not having to, handle things that you don't have to, right? Take care of that undifferentiated heavy lifting and put it on AWS. It also does all the health issues, provides errors via CloudWatch, and then last but not least, the bottom line, which is basically creates the launch configurations, bumps up your auto-scaling group for you, corn downs a node, terminates the instance, and it resets the previous value. It's just really important because if you didn't have something like this, you'd be running your own type of rolling update and so on and so on. Fargate, this is really important just to kind of tell you the limitations and things that you may have to face when you're dealing with Fargate. Fargate, again, it's a serverless compute engine. And so just know that each pod, and by the way, when I say pod or container, I'm kind of using them in the same case, but by the way, a pod is one or more containers. So it's one or more containers. It's the smallest unit in Kubernetes, and I'm going to keep continuously using pod from here on out. But when you are deploying your pod, just know that you can right-size your pod or right-size your CPU memory for your application. Right-sizing is really important here. And at the very bottom is something that's really important as well. You cannot have a daemon set. You cannot have host networking, no GPU support, it can only run within private subnets, and only supports ALBs. That's actually changed. That actually changed about a week ago. You can now use NLBs with Fargate. We just recently announced a new ALB controller that helps support this type of feature, which is NLB to Fargate. If you're wondering how this kind of works with the actual connectivity with Fargate, just realize what we do is we actually will put an ENI into your actual VPC. So if you're kind of new to AWS, this is your virtual private cloud. This is basically your infrastructure, your virtual data center. And basically we put an elastic network interface into your VPC, and we're able to actually connect to it on our side of the infrastructure. And that's how you're actually talking to the pods within the Kubernetes cluster. So it secures that isolation by task. Right size is really important. It's actually really hard to do. And you know what I'm talking about if you tried to do this before. And then last but not least, we do handle that infrastructure for you. Now, this slide right here is kind of talking about how do you actually deploy Fargate with a Kubernetes. This is just a quick example. This is actually using something called EKSCTL. This is actually an AWS defined EKSCTL that helps spin up EKS. But in this specific example, it's actually pointing out that, I'm going to set up a Fargate profile. I'll name it FP default. I'm actually selecting the namespace, which is normally would be default. And then I would go ahead and match and select all the labels and schedule to that Fargate. So this is how you would actually make your Fargate profiles. This is the only addition you would have to actually add to your infrastructure, just to say, AWS, can you please send me a Fargate, rather just than EC2. So let's go ahead and get into IAM. IAM is really important. IAM is Identity Access and Management. And basically, if you're wondering how you start authorizing to your cluster, what you would say is kubectl get nodes. And what happens when you say this, basically you are passing your AWS identity through your credentials, your kube context, to the Kubernetes API. That API will then go ahead and actually make a call to AWS again through that cloud controller. And be like, hey, is Bryan actually part of AWS, and this AWS account? If it is, that's great. What it will then do is send that call back to number 3 on there and actually authorize the AWS identity with RBAC. RBAC stands for role-based access control. Now, if that's the case, and that's who I am, then Bryan is able to do allow deletes, depending on however RBAC is configured. So yeah, that's how you do IAM authentication. And we can kind of look at this a little bit more in depth. If you are not a big Kubernetes users, again, I'm diving in a little bit more. But basically, RBAC is role-based access control, and the config map is where you can actually config some of this. And so you would secure and map your users to the role in the cluster itself. And then you can essentially manage your RBAC along with your IAM permissions. And so when you kind of look at it from this point of view, you actually would do something similar where AWS user authenticates AWS. The user assumes a role based on the access, and then we would have different roles that may have different access, right? You would have a super user, you would maybe have admin, obviously, but what if you just want to read only? And then what you would do to do that is, and I'm just going to kind of show you an example of that. What you would do to do that is you would actually go ahead, you would create an admin role that would be mapped to the cluster within it. So here we actually have a fake account ID. And we would, so this is what we're doing, we're actually just making an assume role. Users would have to have a policy to go ahead and allow them to actually assume the required access, right? So this is what we're showing here. We're just going to go ahead and make the role say Kate's admin. And then we would just create the RBAC group and map it to that Kubernetes role. So if you kind of look through these permissions here, and by the way, if you never really kind of dived into this, we have our API version, right? Well, we're actually just saying the API. Kind stands for the kind of definition of which this specific YAML is seeing itself as. So it's seeing itself as a cluster role binding. The metadata, the name, so we're just naming IAM admin role, the role referral, and this is actually breaking down the cluster admin and the subjects in which you can work with in that group. When you look at this, again, we are now configuring all the things that I just mentioned, right? So this would be on your config map. Notice again, the kind of definition that it sees itself at the very tippity top. It sees itself as a configuration map, and then actually starts breaking down the AWS off the queue system, and actually has inside this file where these permissions are actually allocated to these specific users and that access, right? And then last but not least, you would have to, last but not least, you would actually have to configure the IAM role inside of the actual user's Kubernetes config file. And so this is how you're able to actually go ahead and assume these roles. And this would be inside of your queue context. So, and then that's kind of how you work, right? So that is how you would be able to actually come in, have different users, authenticate with AWS, and actually map these IAM roles specifically to your Kubernetes cluster. So iPod authentication, or IAM podding authentication. So this is always really interesting. We had so many asks for this, and I'm really happy that we came out with this. But basically, this is a way to attach IAM roles to your pods, right? So instead of having, maybe, a wide variety of access, you can actually have fine-grained access to specific pods. So say, for example, you had a pod that is talking to, say S3, and you only needed to talk to S3. You can literally lock down those privileges to those pods and make those pods act on your behalf onto it, S3, and still keep it quite secure. Again, this is a really nice way to have least privilege with your pods, and it's open source. You can actually grab that EKS pod identity webhook, fork it, make your own version. I actually see customers do that sometimes, depending on the complexity of the use case. But yeah, secrets. It's always interesting. There's so many different ways to do secrets. I love HashiCorp's Vault. I gotta hand it to them. It's fantastic. It's one of my favorites. We actually, and again, there's many different ways you can actually use external secrets, which is used with Kubernetes as well. But right now, I'm just going to kind of talk about one of the ways that you could do it with us, which is envelope encryption. So basically, this is the same kind of way. You would actually create a secret. When you write that command, it would hit the API, the Kubernetes API. It would then go and make a data encryption key and encrypt the data locally, right? And locally within your cluster. And then encrypts the data encryption key with KMS, right? If you don't know what KMS is, by the way, that's your key management service. This is basically a way how you can encrypt and decrypt things with AWS and keep your keys in a nice, highly scalable way. It's used all the time. But nevertheless, though, right, you're making a call to that data encryption key and you're actually encrypting it with KMS. And so what happens is when you do that, on the number 3 level, which so we're right here right now, the Kubernetes API will actually persist that DEK, that data encryption key secret into etcd. So what we're basically saying is that that secret we just made, we're storing into etcd. It's on our control plane, and we can't touch it, and no one else can. And that's the nice part about it, because the only one that can is this KMS service, right? And so when you make a call to the secret, what will actually happen is that on the far left side, if someone needs to read the secret, the API server will decrypt the secret with the data encryption key from KMS and actually uncrypt it. So nevertheless, it's a nice secure way. We actually see a lot of customers switching to this just so that they can actually have a highly scalable, manageable secrets. And so this is a little bit of another example. If you're ever kind of curious as well, you can actually use secrets, using secrets with something like AWS Secrets Manager or Systems Manager Parameter or Vault, right? I mentioned Vault a little bit earlier. And so if you kind of look at this, again, you can look at the API up here and what API it's using, the kind of definition that it sees itself, so external secret, the metadata, the specification, right, of this, that this file is, and kind of breaks everything down. But here, you would actually refer to your role, and actually that's how you would be able to fetch your secrets. Again, you're trying to let the roles act on the behalf of you to go and fetch these secrets for you. Networking. So I don't want to fly through. I know we're kind of coming up in the couple of top of the hours, so I'm going to kind of go a little bit quicker, just because there are a couple of things that I said I was going to talk about with my little bio, and I can keep going. I think I think we're 10 minutes late started, but I want to be respectful of people's times. So networking. I was just going to talk about our VPC CNI. Basically, a CNI is a network interface that is basically standardized across Kubernetes clusters. And so what this is it's open source, it's on GitHub, and basically it's how you have networking within your infrastructure. I heard someone say a couple days ago, everyone thinks Kubernetes is nothing but compute. I would say it's half compute, half networking. And so the CNI driver and how it works is basically these pod IPs are from the same pool of IPs, addresses of the VPC. There's VPC native networking with this CNI, so you would actually be using the CNI plugins from your VPC networking. It's simple, secure routing, and it actually supports Calico. And I recommend you use Calico if you need to have networking policy engines within your CNI as well. And so this is a little bit of an example of controlling this network. Actually, this is an example of a network policy. So what you could do with this is actually say, for example, you want to only ingress TCP traffic into any application that says API, right? Or you want to be searching anything from these specific ports, which would actually be Redis here. So you're actually pulling traffic in from Redis. But nevertheless, right, you can actually have fine-grained access to your actual networking policies. And then you can actually do it from external networks as well. This is another example. So you can actually do it from a CIDR range to allow a specific CIDR range or not allow a specific CIDR range. I also wanted to mention that the CNI drivers also allow for advanced networking, meaning that if you actually you can actually communicate with your outbound SNAT to your on-prem environment. So for the enterprise customers here, you probably already know all this, but basically you can actually use your on-premise environment and actually launch nodes into that environment if you need to, or actually get some insight into that as well. Load balancing. So load balancing is always really interesting. Basically, the way that you work with load balancing is by changing your service types to load balancer or ingress object. But what's really important is making sure that you have tags on your load balancers. This is really, really important. And I've actually seen customers having problems with this. You need to automate this as much as you possibly can. But the tags on here would say, okay, I need an ELB or I need an internal ELB. And that's how you would tell your load balancers to go ahead and switch based off of that. There's different types of service load balancers or service type load balancers. This one that you see right here is your simple ELB. Again, we just come back up here, the kind as a service, right? We're looking at the name, we're looking at the specification that this file sees itself as, so we're seeing the type as a load balancer. We're looking for nginx, and we're routing traffic to the target ports 8080, or the port 8080 and target port 80. And so it kind of looks like the image that you see here. So we're following traffic into a node port into the pod. The other type would be an NLB. Now, the NLB, the only thing that you would actually have to change on that deployment would be the annotations up here. And actually sitting here and actually adding NLB would actually switch the load balancer. Instead of an ELB or elastic load balancer, it would switch it to a network load balancer or an NLB. And yeah. Now, when it comes to Kubernetes Ingress, this is a little bit different. This is what the fun part is of Kubernetes. You can do almost anything with this thing. And one of those things is that we needed a better way of having ingress into our Kubernetes clusters, right? And so a Kubernetes Ingress is kind of what you see at the top right. You actually ingress into a cluster and then ingress from there into different specific services. This is where you can have your routing rules, your TLS configurations, your networking. And by the way, I am going to talk about ALBs or application load balancers. Please know there's so many different types of ingresses. I'm just kind of making this a little AWS focus because that's what it is, right? But nginx, F5, hot proxy, I see all of them all the time. And so, yeah. And so here, this is a little bit different. If you look on the far left side and you look back to that picture again, or the ingress YAML that I have in front of you, here we're adding these annotations that actually say that this is an ALB. We're saying that the ALB will be internet facing, which is very important, right? But here on these rules and these HTTP paths, this is where you can actually have a little bit more fine-grained control access, right? You can say, okay, /contact, I can route to a contact pod, like a contact page, right? You can say an API or whatever have you, right? You can literally just do it on the path of your actual URL and funnel that traffic in. And again, what would happen is you can have an ALB funneling to the node port into the pod itself. What is interesting though is sometimes customers need to kind of double up on specific things. And so customers will actually layer ingresses together with an ALB and an NLB, or an NLB and an nginx ingress controller, right? So you're kind of mixing these things around. The lesson here that I would really just take from what I'm about to tell you is just know that you can mix and match your ingresses controllers depending on how you need to use them, right? So sometimes enterprises need static endpoints and wildcards, or maybe there's too many routes for ALBs and they need to do something a little bit different. So what they'll do is they'll actually spin up an ALB or an NLB and then attach to a nginx ingress controller. So just, again, you're doubling up. Okay. Should I keep going? I had a couple more slides. I know I'm up to the top of the hour. What's the feeling right now? Okay, so we were talking a lot. I told you I wanted to deep dive, right? So let's go ahead and get into storage. So with storage, this is always an interesting topic for me because I kind of always not necessarily conflicted. I just want to say, you know, try to make your pods as stateless as possible, right? And what I mean by that is not storing the state within inside of the pod itself. Saying, you know, it kind of goes back to that whole idea of, you know, treating your applications like cattle, not pets, or treating them as grass instead of flowers, right? Basically, if you lost all your pods, you should be able to spin them up instantly and not lose your application, right? If you lost your database, that's a really bad thing, right? That's where your state is or wherever you're storing your information. And so nevertheless, though, it's the real world, right? And you actually have to have some kind of state sometimes. So right now, we actually support EBS, Elastic Block Storage, EFS, which is Elastic File System, and then last but not least is going to be that FSX cluster. Now, what happens is kind of to all the same scenarios that we've been kind of talking about before. Basically, you kind of go into this a little couple of steps. Now, I'm just going to kind of talk from this point of view. I just want to make sure that this is the right one that I was thinking. Okay, yeah. So basically, what this is showing is there's two definitive ways of how you can spin up your storage on AWS. So there's dynamically and statically, right? So this is actually showing the static version. Basically what this is saying is that if you want to use different type of EBS volumes, right? Because if you think back to my original EC2 slides, right, when you were like, why does he have a bunch of numbers on the screen? Is because I want you to right size your applications, right? You only use what you need. You know, none of this stuff matters if this does not help you learn or help your business, right? And so my point is that what you would do as an administrator is you would actually spin up a general purpose 2 EBS volume, or, you know, a cold storage or a tape drive, or depending on whatever you needed. You would have to spin that up first. And then what you would say is, okay, I would like to spin up a pod and actually attach my pod to that EBS volume. Excuse me, I'm sorry. You would actually spin up an EC2 instance and you would actually try to attach to this EBS volume. Remember, because again, everything's kind of disassociated and you're actually able to attach or detach EBS volumes on the fly. So what happens is the Kubernetes cluster will do something called a persistent volume claim. And what that means is that it's claiming this storage, right? If Kubernetes sees this, it will actually take that persistent volume and actually map it together, kind of back to that you know, RBAC controls. So if I say spin me up in EC2 or and an EBS volume, it will go and see if that exists. If it does, and then it will then attach to it. And then there you go. That's how your pods actually has that storage, right? It's also really good because you can detach that EBS volume and switch it around to other instances or whatever have you, right? I just want to say too that this is only from the static way. There's also the dynamic way. So say, for example, if you just want to spin something up and you don't have a persistent volume already there, don't worry. You can just say Kubernetes spin me up EC2 and EBS, and then it'll go and create one and just attach the, you know, the persistent volume to the persistent volume claim. Now, this is the same exact scenario. I'm not going to go through all of that again. The only difference is you would use Elastic File System. And so basically you would go ahead and spin up EFS, and then you would say the same thing. I would like my pods and EC2 instances to go ahead and mount onto this, and it would go and see if that PVC or PV exists. If it does, then it will go ahead and mount together. And then actually, there you go. You now have a stateful workload. And then this is actually, I believe it looks like almost like a WordPress. Yeah, that's a WordPress right there. So that's how you would have an EFS. Now, I always show the screen. I told you I would have this. I show this sometimes because it's just a nice way of helping break down what storages you should be using with your applications, right? So I always show this first. The very top one is a single node with EBS, right? Just remember, you are only in one single availability zone. And if you don't know what that is, this is the collection of data centers that we have within inside of our regions, isolated from fault planes. And so basically you only have your EBS volume into one availability zone. So if something happens to this EBS volume, you might lose all your data, right? Now, if you use EFS, this is where you're going to have multiple, basically a huge file system spanning multiple of these AZs. And so basically, if you lost an AZ, say, Godzilla comes out of left field and takes it out, you still have multiple AZs because they're so far apart and from all fault isolated land. So I really always kind of recommend my customers just to use EFS, especially if you're trying to mount on for multiple pods, right? And actually, that's what the top part's right, basically saying is that you don't want to lose your stateful set, right? Kind of to my point, you don't want to deal with that kind of stuff, right? Sorry, my puppy was attacking my door. Okay. The very last one, though, I always want to point out because it's very interesting, is FSX for Lustre. This is really, really good for like AI/ML, right? And so what you can do is actually have extremely high throughput, and it's a really good way of having multiple nodes for attaching to this access. And just remember, it's usually for these high throughput workloads, and you can actually use data caching with S3. So definitely use that if you can. And it's really, really powerful. So just watch out. I still suggest to use EFS unless you really need FSX for Lustre. And if you need it, by all means. Okay, scaling the Kubernetes clusters. This is always super important. We're almost done, by the way. I think I have two little small sections and I'll stop because I can just go on for 10 hours. But if you're scaling out your applications or your clusters, you are already probably using what is called the cluster autoscaler. And so what happens with the cluster autoscaler, you have to install this into your cluster. But basically what it does is it automatically adjusts the number of nodes in your cluster when a pod fails to launch due to the resources. And so basically what happens is this control plane metric server will continuously keep hitting this autoscaler. And by the way, that autoscaler is attached to that autoscaling group. It's continuously hitting the metric server to make sure it's at a certain point. And then basically the cluster autoscaler will adjust the autoscaling group and actually expand out. So say, for example, you have a ton of traffic coming in, you're some major website and the traffic is just blowing up your Kubernetes cluster. You can immediately tell your cluster just to expand out as fast as possible and then expand back in. Right? When you're done, that's the whole point of the cloud. You don't scale up and just keep it there. You wouldn't keep the house, the water running in your house for 10 days, right? You would turn it off. Same thing with this type of infrastructure. Now that was only dealing with EC2 instances, by the way. And this is, by the way, there's multiple different types of scalers. I'm just kind of talking about the cluster autoscaler, but I believe Zalando has their own, and there's a bunch of other ones. I think Goldilocks as well. The other one, so with the EC2 instances we covered, but for the pods, that's a little bit different. So that we have that layer kind of taken care of. From the pods though, same kind of premise, right? You have some control plane metric server that's being involved. This metric server is continuously looking at the horizontal pod autoscaler, or what is known as HPA. This ensures that the application has proper amounts of instances able to serve. It supports CPU-based scaling or custom metrics. That's really important, the custom metrics part. And so what this is saying is, it's like basically, if I have a bunch of CPU memory utilization being taken out, right, then I can actually start scaling out my pods along with my cluster autoscaler and scaling out my EC2 instances. The thing is too, with that custom metrics, that means that you can actually look at external metrics, right? So one of the more emphasis or more famous type of use cases I hear is I have a bunch of things in my SQS queue. How do I actually expand my cluster based off of the queue? You can do that, right? It's called the Cloud Watch adapter, and you can actually watch any type of metrics to actually scale out or scale in. One thing is too, I always recommend not to use the vertical pod autoscaler in this use case. They just kind of do not work very well together. Yeah, always configure the HPA against the deployment and not the replica sets. The vertical pod autoscaler is a little bit different, right? We were talking about horizontally scaling out. This actually is vertically. This is actually monitors the container metrics and automatically sets the CPU memory considerations automatically. What is really nice about this is it's making sure your nodes are being utilized properly, right? This is a really good way to help right-size your applications with your pods, right? And this is also within a certain amount of resources. It adjusts over time automatically without any manual intervention. I usually kind of see this with stateful sets. So if you say you had a MySQL pod and you need to make sure that it's scaled up correctly, you use a vertical pod autoscaler. That's just kind of depending on the use case and the customer and what I kind of see. But nevertheless, these are just a couple different options for you. Okay, so managing clusters at scale. This is a very large challenge. I cannot tell you how many, how I feel like the community is just all kind of figuring this out together right now. And the way that I have kind of been seeing this is by using something called GitOps. I'm a huge component of GitOps. I think it's the most fascinating thing. And by the way, it's not like a new buzzword. I would say it's kind of like a continuization of DevOps a little bit, or a part of DevOps, if you will. But basically, what this is a way to kind of control your Kubernetes clusters from a pull rather than a push. So long story short, basically you would keep your entire infrastructure into your Git repositories. This Git repository would have your Terraform, this would have your secrets, this would have not your secrets, you'd be using SOPs or Secrets Manager or Vault or something like that. But you would have your YAMLs and everything would be all belonged in Git and all controlled by Git. And then what happens is say, for example, as a developer, you would commit a new change of code. The code would actually get pushed, right? The CI/CD server would do the typical thing that it always does, right? Scan, test, artifacts, whatever have you. But what happens is all it does is instead of push out code, it just updates the configs in Git, right? What that means is what is actually happening inside of your cluster, you're running an agent inside of it. This agent is continuously, just like Kubernetes, it's checking its state, right? But instead, it's checking the state of your Git repository, right? So all you have to do is just change your manifest. It will detect a change and then it will deploy itself. So basically, it's an agent inside your cluster. So what you can do, and I don't have an image on this, I wish I had this up, but what you can do is have, say, for example, one Git repository and 10 EKS clusters. You could point it at that one repository, and then you could spin up all the infrastructure automatically. It's a really, really powerful thing. If you are having problems with config maps or any multi-tenancy or anything like that, I really do suggest looking at GitOps. Flux is actually made by Weaveworks. Weave is a fantastic group of individuals. I really enjoy everything that they do for us and how we work with them. I also would suggest looking at Argo CD. I actually have a demo of Argo running. I was going to show that. Hopefully my demos don't break. But yeah, GitOps is something that I highly suggest to go look at. If you're wondering why the random guy from AWS is spending so much time, it's because I really care about my customers, and I really think this really will make a lot of people's lives a little bit easier to deal with this. Now, I believe this is my last section, and because I mentioned that I was going to talk about spot instances. For anybody that does not know what a spot instance is, this is basically extra capacity. Again, this is my last part. I know I'm hitting on time, but this is the extra capacity that we have within inside of our regions that is currently not being used from the EC2 instance. So basically, you can get our instances up to 90% off. right? The problem is that we will take that instance away from you at any given time, and we're only going to give you a 2-minute window. We'll give you a 2-minute warning, and we actually send that notification through the metadata. But basically, you get 90% off, but at any time, we can take it away from you. So a lot of times customers are like, okay, that doesn't make sense. I have production grade applications, right? Well, what customers will do is you design for Spot, right? And so what you can actually do is you can actually spin up pods while those containers are dying and continuously keep deploying your pods around while you're spinning up Spot instances. And that's what Skyscanner did. Skyscanner was saving a ton of money. And we're super happy that they were able to do that. It is super cool to see customers utilizing Spot instances like this. And so if you're ever curious how you do this, by the way, you can have different mixed groups. Again, this is kind of using the EKS CLI that I mentioned a little bit earlier, but on the right-hand side is more important to this conversation. So you would say, okay, I would like a node group. I would name that node group. I want the size to be only 2, maybe 5, right? The max size. And then I would figure out what price I'm aiming for. And then the instance types that I'm trying to use. I suggest to make a huge net of instances that you utilize, because what you'll find is even the big instances, they might be off, super cheap compared to, say, something like a T2 medium that might be used a lot from other customers, right? So make sure you're really, really picking these Spot instances and trying to save money where you can. And also notice I said that you can have an on-demand based capacity and then also Spot instances. So meaning that you can have a mixture of on-demand instances, so you never go down, and then you can use Spot in the meantime to save money, right? So you basically have 2 layers, kind of mentioning back to the ECS a long time ago, right? A layer of on-demand and a layer of Spot. And then you would actually be handling Spot instances by using something called the AWS Node Termination Handler. And so this is actually automating that notification that your Spot instance is actually going to be taken away, right? And so basically it handles the monitoring of the EC2 instance. It's just continuously watching for these event notifications from AWS saying, hey, we need our Spot instance back. Once it sees that, it will communicate with Kubernetes to properly handle EC2 events when they're received. And then, it will handle core downing and draining the node, handles the maintenance by core downing it, ensures that workflows are still running or scheduled until another maintenance is completed. You should absolutely just deploy this via Helm. So use this. I really enjoy my customers bringing Spot. It's always fun to see these awesome workloads. And I think this is my last couple of tips. Make sure when you're doing Spot instances with autoscaling, same RAM, the number of CPUs. This is just kind of fundamental to cluster autoscaler, how it actually looks at Spot. Leverage Spot Instance Advisor to make sure that you find irrelevant families. Again, to my earlier point, just make sure you find instances that are cheap and are useful for your workload. And then last but not least, diversity. Meaning don't just pick one type of family, try to pick a lot of different families. Thank you. That's all I kind of got. I hope this was great. I know I kind of went a little bit longer, but I know we were kind of started a little bit later, but I hope you all had a good time. I hope this was good.